Thank you, John. Professor Robert Litton is the holder of the Fred J. Benson Endowed Chair in Civil Engineering. Bob helped me out when I was a young professor in the late 70s, and I've never forgotten that. Thank you, Bob. I would now like to ask him to come and introduce Dr. Marcuson. Bob?
It's quite a pleasure and a challenge to introduce Bill Marcuson. The challenge is to try to boil down all of his accomplishments to just a few interesting high points. I hope I've done that. Bill is a native of North Carolina, got his bachelor's degree from the Citadel in South Carolina. After that, a master's degree in civil engineering from Michigan State. After Michigan State, he joined the world's largest fraternity and spent a couple of years on active duty with the U.S. Army Corps of Engineers, where he was a platoon leader and a company commander. After the military, he went to North Carolina State and got a doctor's degree there. When he got finished with the PhD, he joined the staff at the U.S. Army Waterways Experiment Station in Vicksburg. That was 1970. And by 1981, he became the director of the geotechnical lab there at WES. He was the director from 81 to 1999, and as of January the 1st of this year, he has become an emeritus researcher of the Waterways Experiment Station and a consulting engineer. He's registered in Mississippi and South Carolina and is a chartered engineer in England. He has a wide variety of responsibilities that he discharged during that entire career there at the Waterways Experiment Station, including research and development, analysis, forensic investigations, and so on and so forth. And in a wide variety of fields, including soil and rock mechanics, earthquake engineering, geophysics. I got to turn the page here. I couldn't get it onto one. Geophysics, engineering, geology, military pavements, and a very interesting area of mobility. All of this research, field research, laboratory research, analysis was conducted both in the United States and overseas. Just reading through the resume is quite an adventure. Many of the things that he's been responsible for and been deeply involved in. Of course, all the energy that he's expended has resulted in awards and distinctions which are frankly too numerous for me to mention. But I do want to mention a few, like the American Society of Civil Engineers Huber Prize that he won, and then in 1997, the Norman Medal. The National Society of Professional Engineers named him the Federal Engineer of the Year back in 1995. In 1996, he was elected to the National Academy of Engineering. And he is currently the Vice President of the American Society of Civil Engineers in Zone 2. And there are several other things, professional activities that he's involved in that I told him I would leave him a little bit of time to present his lecture here after this introduction, so I better aim for that termination of my introduction. He's seen a lot. He's been involved in a lot, and at all levels of involvement. This has given him a wide range of experience and a rare overview of the relationship between soil mechanics in its broadest sense and United States national defense, which is the subject of his Terzaghi Lecture, another of the distinctions that he's been awarded and which he gave last year, 1999. I would ask you to give a warm welcome to Dr. Bill Marcuson.
Bob, thank you very much for that kind introduction. It is indeed a pleasure for me to be the warm-up speaker for the Spencer J. Buchanan Lecture. And In that sense, I need to tell you that Spencer J. Buchanan came to the Waterways Experiment Station about 1937 and was the first director of the geotechnical lab at the Waterways Experiment Station. And on the wall of the Casa Grande laboratory, the first picture you see is Spencer J. Buchanan. And it's the same picture you see in your handout in Harry's publication. The second is W.J. Turnbull. The third is James P. Sale. And now the fourth is William F. Marcuson. But I'm delighted to be at Texas A&M and to be part of the Spencer J. Buchanan lecture as the warm-up show. I was deeply honored to be invited to present last year's Terzaghi Lecture because of the stature of the lecture as established by those distinguished engineers who preceded me. Unlike most previous Terzaghi lectures, I never knew nor worked with Karl Terzaghi. I was fortunate to have known and worked with two of his students, M. Yule Vorsleff and Arthur Casagrande. These and other outstanding geotechnical engineers impressed upon me the usefulness of history, tradition, teamwork, and symbiotic relationships. It was with these thoughts in mind that I chose the topic, Soil Mechanics and the U.S. National Defense, a mutually beneficial relationship, for this lecture. I think the term military-industrial complex was coined during the Eisenhower administration. What I'm going to speak about this afternoon is the operation of the military-industrial complex and the fruits it has generated and will continue to generate. This is a roadmap of my presentation. I've been fortunate. I've had a long and fulfilling career with the Waterways Experiment Station, the premier civil engineering laboratory in the United States Army. This afternoon, I'm going to concentrate on military research as opposed to civil works research. My reason for this is that I believe most of you in the audience are aware of the contributions that the Corps has made to water resources. What I'd like to concentrate on, I believe, is not so well known. I don't want to leave you with the impression that the Waterways Experiment Station was the only player. We were not. And I need to tell you that I'll talk about the Waterways Experiment Station, WES, and the station all as the same synonymous organization. So if I say WES or I say the station, it's all the same. There were and are a number of other players. From the government side of the house, they include the Engineer Research and Development Lab, which was part of the Corps located at Fort Belvoir. In the Air Force, there's the Air Force Weapons Lab located at Kirtland Air Force Base near Albuquerque. And the Naval Civil Engineering Lab, now named Naval Facilities Engineering Services Center at Port Hueneme near Los Angeles. And of course, the Defense Atomic Support Agency, now named the Defense Threat Reduction Agency. This afternoon, I'm going to concentrate on a period just prior to World War II, to today. If you look back in history, you'll see that engineers and scientists searched in vain for mathematical equations and soil mechanics formula that would allow the prediction of expected soil behavior with theoretical underpinning. In 1720, the French government created the Corps of Engineers of Bridges and Roads, the first government organization dedicated to civil engineering. Much of Charles Augustin Coulomb's work was related to military fortifications. Coulomb's theory of earth pressure on lateral supports was founded on the assumption, and I quote, "Failure of a laterally supported bank occurs as a result of shearing resistance of the earth being exceeded along a surface of sliding," end quote. From this, he derived the first mathematical formula intended to predict soil behavior in a theoretical framework. Since this was done for the French military, I argue that the military was a critical part of the birth of soil mechanics. During this presentation, I will demonstrate to you that the military has played, is playing, and will continue to play an important role in making contributions to soil mechanics and geotechnical engineering. In fact, how many of you in the audience know what was the first engineering school in the United States? West Point, founded in 1802, and in fact, in 2 more years, they will celebrate 200 years. Now, let's go to a period just prior to World War II. During 1936, seepage problems threatened the integrity of Franklin Falls Dam, an earth structure located in New Hampshire. A major investigation ensued. Arthur Casagrande had recently published his findings on his investigations of fine cohesionless soils, a report that caught the attention of Captain James H. Stratton of the Corps' Boston District. On Stratton's recommendation, the Boston District hired Professor Casagrande as a consultant to investigate the critical density of the fine sand in the dam's foundation. This marked the beginning of a relationship between the Corps of Engineers and Arthur Casagrande that lasted until his death in 1981, and that relationship, possibly as much as any single factor, shaped the future of soil mechanics in the Corps. As World War II approached, no area of military R&D was more vital than that involving airfield construction, largely because technology in the area lagged far behind the requirements of the time. Before the wartime emergency, commercial planes of 25,000 pounds gross weight, having wheel loads of up to 12,500 pounds, were the heaviest in use. As late as 1939, the U.S. Army Air Corps assumed that in the event of war, all planes, except heavily loaded bombers, could operate on sod fields. In 1940, while Nazi Germany overran France and threatened to invade England, the Army had yet to develop criteria for paved runways, and virtually no concept existed as to how to design runways for wheel loads exceeding 12,500 pounds. Yet, bombers were being developed with wheel loads of 37,000 pounds, and far heavier ones were coming into use. Thus, the Corps of Engineers inherited a complex and urgent problem. At that time, the Corps identified airfield paving design as essentially a soil mechanics function. Engineers recognized that the primary problems in air-based paving was the failure of the soil subbases under pavements to withstand the loads, resulting in the failure of the pavement. Corps leaders acknowledged the gravity of the situation, and T.A. Dad Middlebrooks of the Office Chief of Engineers had by early 1942 become impressed with a method developed in California by O.J. Porter to calculate the bearing capacity of soils under pavements. The penetration test was essentially a shear test, measuring the strength of the soil, while the bearing capacity was an index of that strength. Upon calculation, the bearing ratio was referred to as the California Bearing Ratio, or CBR, which provided a quantitative expression of the strength of the soil. Whether the CBR could be adopted and adapted to the complexities of airfield paving was debatable. In February of 1942, Middlebrooks asked Porter to come to Washington, D.C. for discussions about the CBR. After days of fruitless deliberations, they found their ideas far apart. Lieutenant Colonel James H. Stratton then telephoned Casagrande soliciting his input. Casagrande knew nothing of the CBR and was forced to act as a catalyst. He immediately proceeded to OCE headquarters, where he talked at length with Porter and Middlebrooks. In a monumental decision, the Corps of Engineers adopted the CBR as the anticipated basis for future airfield pavement design. This picture was taken at the Stockton Test Track in Stockton, California. The front row is a Colonel Henry C. Wolfe. This is Harold M. Westergaard, the Dean of Engineering at Harvard. This is Philip C. Rutledge, who at the time was at Northwestern University and later with the firm Muser Rutledge in New York. This is Arthur Casagrande. This is Dad Middlebrooks. This is James L. Land. And this is O.J. Porter. As an aside, I should tell you that the James H. Stratton I've been referring to is the man who was the principal in the firm Tibbett, Abbott, McCarthy, and Stratton, known today as TAMS Consultants with headquarters in New York City. Before I leave this slide, let me also mention that OCE embroiled WES in this controversy, and by the end of 1942, WES found itself at the forefront of flexible pavement research in the entire Corps of Engineers. With the U.S. immersed in World War II, Arthur Casagrande dedicated himself further to the war effort. In 1942, he volunteered to the Chief of Engineers to establish a 6-week course in soil mechanics, concentrating on airfield pavements for Army officers. The resulting Army Soils Control School accepted its first class of 24 lieutenants at Pierce Hall on 3 July 1942. 3 July, do you get a sense of urgency? My guess is if we were doing it today, we'd started on 5 or 6 July. This is a picture of the original class. This is Arthur Casagrande. This is Ralph Fadum, who died last July, but he was dean of the School of Engineering at North Carolina State during the late 60s when I was there. I do not know who this lady is, and if there's anybody in the audience who can tell me, I'd appreciate it if you'd come up to me and tell me who the lady is. But that's Joe Compton. Joe Compton also died last February during Engineer Week. And I noticed in reading through the yellow book in front of you, Joe Compton is a supporter of the Buchanan Lecture. Joe had a degree in business from the University of Virginia. He later took courses, engineering courses at Harvard and at MIT, and he became one of the leading figures in the development of soil mechanics and military environmental analysis at U.S. Arthur Casagrande and Karl Terzaghi, who had come to Harvard in 1939, conducted classes personally in a demanding 8-hour-a-day schedule that included classroom lectures, laboratory sessions, discourses by outside speakers, and field trips. From a seemingly infinite variety of samples from his Harvard laboratory, Casagrande would feel each soil, roll out a thread in the palm of his hand, taste it, bite it, rub it between his fingers, estimate its strength, and finish with a description of its probable source, suitability for airfield construction, potential problems, and estimate its Atterberg limits. His assistant, and that was Stanley D. Wilson, invariably found his estimates to be nearly as precise as the laboratory determined values. Harvard continued to sponsor the course until 1944, producing about 400 graduates. As these graduates and their careers progressed, they moved to important positions throughout the Corps and the Army, providing Professor Casagrande with an important network. This allowed Casagrande to have what I'd call maximum influence on technical subjects involving soil mechanics within the Corps of Engineers. In 1942, the 40-year-old Casagrande devised a new classification system that he incorporated into his Harvard courses. By year's end, the Corps had accepted Casagrande's airfield classification system as the standard for military construction. Casagrande developed the ASCE system as a rapid method for identifying and grouping soils for airfield construction. I am told he was particularly pleased because the ASCE system also contained his initials. Continued evolution of the ASCE system after the war, largely at Harvard and at U.S., led to the adoption of Casagrande's unified soil classification system as the most widely used in the field today. Now, this is a table taken directly from a text entitled Introduction to Soil Mechanics and Foundations by Sowers and Sowers. And I just want to read for you the caption under the title, but it says, after U.S. Waterways Experiment Station. This is a plasticity chart, again, taken from a text by Sowers and Sowers. And again, let me just read the acknowledgments at the bottom. And it says, after A. Casagrande and the U.S. Army Waterways Experiment Station. All of this grew out of our country's needs for airfields in World War II. The Unified Soil Classification System may very well be Casagrande's greatest contribution to soil mechanics because of its wide and important use in the practice of geotechnical engineering today. Airfield designers had long recognized the importance of compaction of base and sub-base materials prior to paving, especially where flexible pavements were to be used. However, no systematic analysis of compaction requirements had been performed for airfields prior to the end of World War II. In May of 1945, OCE authorized a comprehensive soil compaction investigation, and in June assigned the testing to U.S. Immediately, project directors A.A. Maxwell and Cecil D. Burns, both engineers at U.S., attempted to locate materials in the vicinity of Vicksburg. A source of material was found, and a mixing plant built on location blended soils from a pit in large quantities, and these were spread by drag lines onto 200-foot-long test lanes. Drivers then passed various compaction machines repeatedly over the lanes. This is a slide of an early sheep's foot roller. Researchers varied the water contents of the soil, the number of passes, the types of machinery used, and other components in a complex series of tests. Field and laboratory examinations determined compaction and CBR data that were produced by each set of variables. From this, specific compaction expectations and methods under field conditions could be predicted for future construction. In April of 1956, W.J. Turnbull and Charles R. Foster published their seminal paper entitled Stabilization of Material by Compaction. This was also later published in the Transactions of ASCE in 1958. Let me now read from the synopsis of that paper. A soil can be stabilized by compaction at proper water content. This paper shows the relationship between strength and both water content and density for cohesive soils, and it describes the variation in density and strength produced by variations in rolling and lift thicknesses in field compaction. These are some of the data presented by Turnbull and Foster, and across the bottom you have water content. You've got unsoaked CBR and dry density, and this is for 6 blows per layer, 12 blows per layer, 26 blows per layer, and 55 blows per layer with a 10-pound hammer falling 18 inches. This is another picture from the Turnbull and Foster paper, and again across the bottom you've got number of passes up the side, maximum dry density and optimum water content, and we're looking at, if you will, sheep's foot rollers with a 7 square inch foot, a 14 square inch foot, and a 24 square inch foot. Let me now just quote from the acknowledgement section of the paper. The studies described herein were conducted under the Office Chief of Engineers as part of an overall development of design criteria for airfield pavement for the United States Air Force. Gail McFadden, Thomas Pringle, and F.B. Henian of the Airfields Branch of the Office Chief of Engineers monitored this study, for which guidance was furnished by Arthur Casagrande, Donald W. Taylor, Kenneth B. Woods, O.J. Porter, and Philip C. Rutledge, acting as consultants. The laboratory and field work were accomplished by the Flexible Pavements Laboratory of the Waterways Experiment Station. John Fote discusses the paper. And let me thank John for coming. John will have heard this lecture twice, and I think my wife is the only one who's heard it more than twice, but Margaret says it gets better every time. John, I hope you think so too. John also discusses the paper, and he flags the point that moisture content is certainly as important as density control. Fote states that engineers should determine why compaction is desired, what he or she wants to achieve with it, and how he or she intends to accomplish it. Before leaving the topic, let me mention that Turnbull and Foster received ASCE's Norman Medal in 1959 for this work, and that John Fote worked at the Waterways Experiment Station in the late 40s and early 50s. This changed his life in a number of ways, one of which is he met Edith Riles, a local school teacher, fell in love, and married her in Vicksburg at Gibson Memorial Methodist Church on August the 8th, 1950, some 50 years ago. Before leaving the topic, let me say that I think This forms the state-of-the-art in compaction of base and sub-base materials for airfields as we practice it today. Prior to World War II, soil mechanics had been concerned primarily with the behavior of soils under static loads. Dynamic loads such as vibrations by machines shaking their foundations or shocks from earthquakes or explosions presented a difficult and challenging problem. Early studies in the area were tentative. In the late 1940s, W.L. Shannon and Arthur Casagrande performed the first dynamic tests on soils in the United States at Harvard. These stemmed from the fear of the effect of nuclear blast at the Panama Canal. Soil dynamics attracted relatively little attention until the 1950s, when the proliferation of long-range missiles carrying nuclear warheads capable of producing massive ground shocks aroused new concerns. I'll now briefly cover work, both analytical and laboratory, that was conducted in the early 1950s. During the early 50s, or during the 50s, Professor Newmark and his colleagues at the University of Illinois conducted research involving the design of underground protective structures. Much of the work involved the conduct of experiments to aid in the development of numerical methods that could be used to design underground nuclear protective structures. The testing was conducted by the Defense Atomic Support Agency, primarily at what we now call the Nevada Test Site outside of Las Vegas. And let me just call your attention to the center report here, published in 1956, entitled Designing for Nuclear Blast Protection. That's a live load most structural engineers prefer not to deal with. Strategists in the United States during this period also feared the impact of near-miss nuclear explosives on strategic defense systems such as underground missile silos. The thought was that if we have an underground missile silo and it gets a direct hit, we will sacrifice that. But if it gets a near miss, we'd like the bird cage to open and the bird to get out. To supplement the field projects, OCE in 1951 turned to Professor Donald W. Taylor at MIT to perform a laboratory investigation on the response of soils to rapid, intense loading. During this study, Robert V. Whitman developed a large triaxial testing machine that produced a single rapid loading on samples in an attempt to simulate the shock of the explosion. And if you're really interested in knowing more, I would call your attention to the paper by Whitman, Behavior of Soils Under Transient Loading, Proceedings of the 4th International Conference on Soil Mechanics, 1957. Now, in 1957, OCE placed West in charge of future studies in the area. Turnbull continued the contract at MIT to perform another series of laboratory investigations, which was completed in the late 1960s and produced some 27 reports. Robert V. Whitman was the principal investigator on this contract, and this slide shows 4 typical report titles. One dealing with the shearing resistance of sands, rapid loading, one on wave propagation velocity, another on stress-strain time behavior, and a 4th on the response of soils to dynamic loading. Let me show you 2 figures now that are in Bob Whitman's last report on the response of soils to dynamic loading. But actually, Bob Whitman took the figures from a report by Carl Constantino, who is a professor at CCNY, City College in New York. But this is a plot of horizontal displacements at a radial distance from the blast of 1,550 feet. This is time in milliseconds. And this is horizontal displacements. But what I want you to notice is the displacements are minus and plus 2 inches. And we're talking about 2 inches of displacement, plus or minus 2 inches. This is another figure from Whitman's report taken from Constantino. But again, this is ground zero. This is range from ground zero in feet. And this is depth in feet. And we're talking about a crater with a radius of 350 feet. The purpose of showing you this is just to give you an example of the sort of problems the Department of Defense was studying at the time, both in terms of intensity and rate of loading. During this same period, parallel work was ongoing at other universities, the University of Illinois notably, and that's the one I'm going to highlight today. And I'd like to highlight a report entitled Energy Absorption Capacity of Granular Materials in One-Dimensional Compression by A.J. Hendren, Jr. and his colleagues at the University of Illinois. The work was done for the Air Force Special Weapons Lab at Kirtland Air Force Base. And let me just more or less quote, I'll paraphrase from Skip's report. This is just a schematic stress-strain curve with strain across the bottom and stress up the top. But Skip says, as the stress continues to increase in the neighborhood of 1,000 to 5,000 psi, the contact forces become so large that particles begin to crush. The crushing is accompanied by a certain amount of rearrangement that is reflected in the concave downward stress-strain curve shown in region 3. Energy is absorbed in this range by the creation of new surface area during crushing, and energy is dissipated as heat due to rearrangement of the new particles into a denser configuration. Both of these mechanisms absorb energy, which is no longer in the form of recoverable strain energy. This work was published in 1963. And again, the point I'm trying to make is that in the early 1960s, there was a great deal of study ongoing with regard to soil properties, particularly dynamic soil properties, dynamic nonlinear soil properties at rapid, intense loadings. Because of time constraints, I'm not going to cover all the work that went on at that time at various locations, including WES, to predict dynamic response of underground structures. But I believe that this work greatly influenced the way we approach dynamic soil structure interaction problems today. Now let me change subjects slightly. Difficulties with Nike Zeus tracking radar systems located at White Sands Missile Range, New Mexico, caught the attention of foundation specialists in the early 60s. Unexpected movements resulted in sudden changes of direction or stopping of the radar trackers as they located targets, and further vibrations occurred as the antennas developed precise focus on missiles after launching. WES was asked to investigate the problem. Primary responsibility for this study fell on 2 engineers and a scientist, Robert Ballard and Z.B. Fry. This is a slide of the radar tower. Notice the circular foundation or footing. WES modeled these footings and conducted model tests both at Vicksburg and Eglin Air Force Base. This picture depicts one of those model foundations. The forcing function was provided by an eccentric mass vibrator that had been used by the Navy to test ships in World War II. The Navy first loaned and then gave the device to WES. Weighing 5,600 pounds, the cumbersome machine and its large electric generator had to be moved by a crane. It could, however, simulate motions in 3 directions: vertical, torsional, and rocking. Placed on a circular concrete base at West with varying static loads, it applied a dynamic load of 20,000 pounds. Using the Navy machine as a model, West designed a scaled-down version with a hydraulic motor capable of generating 3,600 pounds of force. The mobile apparatus shown here was trailer-mounted, pulled by a truck, and could operate on power generated by the truck engine. Its primary purpose was in the determination of Rayleigh or shear wave velocities to a depth of about 100 feet. Now, you've seen this slide once before. Last time I called your attention to the round circular base. This time let me bring your attention to the West truck that's located at the base at the front right. This work, West worked with a group of consultants named on this slide to provide advice and assistance. Whitman, Richard, and Lydink Jacobson proved especially helpful. Many of these consultants took the West data back to campus and developed theoretical and analytical approaches for predicting dynamic footing response. For example, I'd refer you to a paper entitled Footing Vibration with Nonlinear Subgrade Support by Funston and Hall. Let me also just highlight 3 other important papers that came out of this investigation. One entitled Dynamic Response of Footings to Vertical Loads by John Leismer and Bill Richard. Another entitled Comparison of Footing Vibration Tests with Theory by Bill Richard and Bob Whitman. And a third, Design Procedures for Dynamically Loaded Foundations by Bob Whitman and Bill Richard. These 3 papers were published in the ASCE Journal in 1966 and 1967. This figure shows a uniformly loaded half space and what we now call a Leismer analog. Let me now show you a couple of figures taken from the Richard Whitman paper of '67. Again, this shows a vertical oscillation comparison for test results in theory. The dots are West results. The smooth curves are theory. This is another plot, a comparison of amplitudes of motion for torsional oscillation. Again, the open dots are from tests from Eglin Air Force Base. The closed dots, or black dots, are from the Vicksburg site, and this is theory. Some of you might not think that's such hot prediction, but it's not bad for soil dynamics. This figure was taken directly from the paper by Whitman and Richard and shows a typical equivalent lump mass system for horizontal excitation. And this figure comes out of the Leismer-Richard paper, and it shows a log-log graph, a comparison of computed and measured vertical amplitudes. And if everything was perfect, all the data would plot on that line, which is 1. And you'll see the data plot largely between 1/2 and 2. And so for all practical purposes, the comparisons are within a factor of 2. Much of this work led to a book entitled Vibration of Soils and Foundations by Richard, Hall, and Woods. I argue that this work represents the state of the art in the design and analysis of dynamically loaded foundations today. The research confirmed radiation damping. Before this work was completed, people always assigned a large participating mass to the system. This work greatly reduced the size of that participating mass. In the last 30 years, we have incorporated the effects of embedment, and we have expanded our methods to include geometries other than circular. But that's it. In preparation for this Terzaghi lecture, I tried to determine the origin of the term rock mechanics in the United States. So far, I've been unsuccessful. Clifton W. Livingston is credited by some as being the father of rock mechanics in the United States. Livingston was head of the Department of Mining at the Colorado School of Mines during the 1950s. One of the first publications on the field we now know as rock mechanics is entitled An Introduction to the Design of Underground Openings for Defense. This was published in volume 46, number 1, of the Quarterly of the Colorado School of Mines, and it's dated January 1951. The volume was compiled by Clifton W. Livingston and edited by Leroy W. Goodwin. Nowhere in the volume can I find the term rock mechanics. The first symposium on rock mechanics was held in July 1956 at the Colorado School of Mines. Consequently, I believe the term rock mechanics was coined in the early 50s, and I believe the Department of Defense played an important role in the formation of the field that we now know as rock mechanics. The group of papers presented in the volume of the Quarterly of the Colorado School of Mines discusses the design and construction of underground openings subjected to bomb bursts. The Missouri School of Mines, now known as the University of Missouri at Rolla, Penn State University, and the University of Minnesota were other early players in the field of rock mechanics. Much of the research being conducted in the 1950s was directly related to our national defense and the fear of nuclear weapons effects. As I previously mentioned, Professor Newmark and his colleagues at the University of Illinois were heavily involved in soil structure interaction problems related to high-intensity, rapid loading. Much of the work was part of the Nuclear Weapons Effects Research Program sponsored by the Defense Atomic Support Agency, later called the Defense Nuclear Agency, and now named the Defense Threat Reduction Agency. During this period, the United States was interested in constructing large underground cavities on the order of 120 feet in diameter. At a meeting with the Defense Atomic Support Agency, doubts about the constructability of such caverns at NTS were expressed. These doubts stemmed from the size of the cavern with respect to the rock's low strength with respect to the ground stresses, the vertical stresses, the overburden pressure. Professor Deere at the University of Illinois was a consultant to Phoenix and Sessom, the firm that was responsible for underground design at the test site. Phoenix and Sessom, based on Deere's recommendation, supported the concept, and it was approved to be built. After approval, Phoenix and Sessom turned to Professor Deere and said something to the effect, "We followed your advice, now let's make it work." If you were from Texas A&M, you'd probably say, "Put your money where your mouth is." Two of the cavities, approximately 100 feet in diameter and 150 feet high, were constructed at a depth of 1,300 feet in very weak tuff of excellent rock mass quality. A third cavity, approximately 60 feet in diameter and 80 feet high, was constructed at a depth of 350 feet in jointed granite of high impact strength and fair to good rock mass quality. Now, this is a slide of the two cavities constructed at 1,350 feet, cavity 1 located here, cavity 2 here, and the access portal was a 4,700-foot long tunnel that entered at the side of Rainier Mesa. The cavities were approximately hemispherical in shape, between 60 and 75 feet in diameter. Excavation started from the tunnel on two rises that were inclined at angles of 68 degrees. The top was domed to prevent stress concentration. Excavation was by blasting, followed closely by rock bolts. This was one of the first uses of rock bolts in the United States in large caverns. Professor Deere's man on the site from December 1964 to June 1965 was Edward J. Cording, both a graduate student at the University of Illinois and a mining engineer with Phoenix and Sessom. In October of 1965, Lieutenant Cording was assigned to U.S. And during the period October 65 to July 66, continued his doctoral research. In July 66, Lieutenant Cording departed Vicksburg, headed for Vietnam with his entire dissertation in a plywood footlocker constructed by carpenters at the Waterways Experiment Station. As an interesting sidebar, Ed Cording stopped by the University of Illinois for a day before shipping out to Vietnam. Professor Peck suggested that he take his final examination that day. Deere thought it was a great idea, and they assembled his committee. The thesis was defended that afternoon. The paperwork was to go forward once the thesis was completed. Cording completed the final chapters of his thesis in Vietnam, sending them handwritten to Wes. Wes typed and assembled the thesis. Professor Peck and Deere reviewed the thesis, and M.T. Davison walked the paperwork through the University of Illinois. Captain Edward J. Cording received his Ph.D. in June of 1967 while on R&R in Malaysia before his tour in Vietnam ended. His dissertation, The Stability During Construction of 3 Large Underground Openings in Rock, was published by Wes. During this period, Wes had a number of active duty personnel. Some, like Ed Cording, were also graduate students assigned to Wes completing their dissertations. A list of some of them is shown here. This list is not complete, but I think it does list everybody that was assigned to Wes as an Army officer that worked on strictly military projects. But let me mention some names of people who have worked at the Waterways Experiment Station that are household names in the geotechnical community. I'll start with George Osterberg. I've already mentioned John Fote, Jim Mitchell, Mike Duncan, Wayne Clough, and Skip Hendren. I'll stop there because I don't want you to think that all the good ones left. If you will, let me fast forward to the 1980s when the Air Force Ballistic Missile Office was interested in conducting a study evaluating the effectiveness of rock bolts of various lengths. W.O. Miller, and I know him as Yogi Miller, an engineer at Wes, designed and fabricated a polyaxial load frame to conduct physical models of experiments of rock-bolted tunnels. The work involved the development of a large-scale facility, the development of suitable rock simulant, the development of scale model rock bolts, and the testing of model tunnels. This slide shows the partially assembled polyaxial load frame. This slide shows an exploded view of the loading frame showing the model tunnel, and the model tunnel is right there, and the flat jacks. This shows the orientation of the flat jacks around the specimen, and it shows that we can vary sigma 1, sigma 2, and sigma 3. This shows a model of a tunnel with 9-inch rock bolts in the loading frame, and we actually poured the simulant, or the rock simulant, in the frame, and you'll see the loading frame right there. We poured it in like concrete. This slide shows the extensiometers for measuring tunnel closure, and we define tunnel closure as the change in radius divided by the radius, or the change in diameter divided by the diameter. And this slide shows a tunnel after testing. This slide shows the removal of a 30,000-pound test specimen. And this slide shows the influence of rock bolt lengths on tunnel closure. If you will, this is a normalized shear strength. This is rock bolt length divided by tunnel diameter from 0 to 3/4. And this is tunnel closure, 1%, 2%, 3%, 4%, 5%. And you see you get more stability at a rock bolt length of about 1/4 of the diameter. If you think about this a little, if you've got a long rock bolt, this end is fixed, this end is moving, and the rock bolt fails in tension. If you have a shorter rock bolt, both ends can move and you can get more deformation before you get the ultimate strain. The tunnel also deforms as a thick wall cylinder. Much of this work formed Miller's PhD dissertation here at Texas A&M, and it yields a design scheme for more stable tunnels and the potential for saving up to $5 million per mile of tunnel construction. I should mention that Miller's research was targeted at high stress, low strength rock tunnels. This is deep tunnels in weak rock. The relationships are not necessarily the same for lower stress, higher strength rock tunnels. Now, up until now, I've been talking about the past, and I'm a whole lot more comfortable talking about the past than I am the future. But I'd like to talk just a little about the future. I've tried to make the point that WES has a long history in conducting scale model and full-scale experiments. I've mentioned field test sections that were constructed to study compaction, full-scale test conducted at Nike Zeus radar towers, and vibration tests conducted of scale model circular footings, and full-scale studies of rock-bolted underground structures, scale models of rock-bolted tunnels tested to failure. Such studies are complex, important, require a team of people, expensive, and sometimes critically necessary to understand the phenomena and behavior in complex situations. And I would argue that the government is uniquely situated to conduct such experiments. These are exciting times, times of rapid change and an increasing rate of change. Some of you in the audience are aware that the Corps has recently reorganized its R&D community into the U.S. Army Engineer Research and Development Center. The acronym is ERDC, pronounced ERDIC, with headquarters at Waterways Experiment Station. When we were trying to come up with a name, a number of us wanted to call it the National Engineering Research and Development Command. The acronym would have been NERDCOM. Our wives thought it was particularly appropriate, but we couldn't find anybody in the Army that would command it. There are a number of laboratories, many of them at the Waterways Experiment Station, but we have the Cold Regions Research and Engineering Center located in Hanover, New Hampshire, the Construction Engineering Lab located near the campus of the University of Illinois, and the Topographic Engineering Center located at Fort Belvoir. But all of these come under ERDIC now, which is headquartered in Vicksburg. ERDIC has many unique facilities. I'll show you 4 typical examples listed here. This is a slide of a 3-dimensional 12-foot by 12-foot shake table located at the Construction Engineering Research Laboratory near the campus of the University of Illinois, capable of shaking models that weigh up to 60 tons at a frequency range of 1.5 to 15 hertz with displacements of up to plus or minus 6 inches. Our Cold Regions Research and Engineering Laboratory, and I shouldn't say our anymore, because I've retired, but nevertheless, we have a heavy vehicle simulator located inside a frost effects laboratory where one can investigate the freeze-thaw cycles of pavement systems under simulated real-world conditions. Shown here is our centrifuge, capable of conducting model studies of up to 350 Gs, using models that weigh up to 8 tons. And you've already seen our polyaxial loader at the Waterways Experiment Station, capable of conducting various model studies. These and other facilities poise the core to move the Army to the Army of the future. And until recently, we call that the Army After Next. The vision includes such items as a 1 million-pound aircraft, vehicles capable of moving across the battle space at 100 miles an hour, and technology for homeland defense. I've mentioned that in the past, we've had relationships where graduate students came to WES and other core labs, many times on active duty, and participated in research and completed their dissertations. The Corps of Engineers currently has a memorandum with the National Science Foundation. This document is dated 29 March 1996 and allows academic researchers and their graduate students the use of facilities at Corps laboratories on a reimbursable basis. I have a vision in which the National Science Foundation and perhaps other government agencies could develop a pool of money such that these facilities could be made more or less free to academic researchers and their graduate students. I say more or less free because things that are truly free are not highly valued. Consequently, I'd like the people who use these facilities to pay their own travel and their own per diem. The concept can be expanded to include private industry. For a relatively small amount of money, these facilities could be made available to the public for research. Proposals would need to be evaluated and ranked by appropriate committees. Once accepted and prioritized, the highest priority experiments could begin. The core labs would provide office space, computers, telephones, equipment, and technicians and engineers needed to assist in the conduct of the experiments. Once completed, the experimental results would become public information and could be put on the net for the world to analyze. There would have to be one caveat, and that is if the Department of Defense had an urgent national need, we'd break in line and conduct our experiment as required. Such a venture is a win-win situation for everyone. It allows public access to equipment that would otherwise be unavailable. It provides maximum use of DoD facilities that would otherwise go underutilized. And in the last year, discussions have been initiated with NSF to make this become a reality. And the hope is to have it in place soon. During this presentation, I've painted a picture of cooperation and synergy among the government, private sector, and the academic community. This has been a team effort, one of engineers working together to address critical issues of our nation and our national defense. Now let me briefly discuss 2 or 3 areas of research with a high potential for future payoffs. A current vision in the Department of Defense is to have a rapidly deployable, self-sustaining expeditionary force. And for you Marines in the audience, I'm not using expeditionary in the doctrinal sense. Such a force could be deployed anywhere in the world, carry out its mission without dragging a large logistics or sustainment tail behind it. From a geotechnical engineering viewpoint, this will require maximum use of indigenous materials for construction, repair, and maintenance of field fortifications, in theater of operation roads and airfields, or in the battle space roads and airfields, and lines of communication. Let's just focus on the use of indigenous material for construction, repair, and maintenance of in-theater roads and airfields, and the potential benefit the results of this effort will have on the private sector. If we're successful at developing methods to use low-quality or out-of-spec materials for repair of transportation infrastructure, the application of this technology could potentially save billions, that's billions with a B, of dollars as we go about repairing our transportation infrastructure in the United States. Much of the future training of the armed forces will be conducted using computerized war games and simulators. The natural environment must be understood and characterized, and we're a long way from there. These requirements will drive engineering technology in the future. Another Army requirement associated with creating a virtual battle space environment for training purposes is what I call putting engineer activities into the models. For example, what is required and how long will it take for an infantry battalion to cross a given river at a given location if the bridge is destroyed? Again, if we're successful at creating a realistic, dynamic, synthetic, natural environment and accurately modeling the engineer activity, imagine the spin-offs that this will have for the civilian engineer and the construction community. For example, large, complex construction projects such as the construction of a dam could be completely rehearsed, and project managers could plan and manage staffing and material requirements as a function of time more effectively than ever before. In a sense, the point I'm trying to make is something that many geotechnical engineers already know. Our computerized capabilities have far outstripped our site characterization capabilities. Thus, if we're to exploit our computational methods, we need to accelerate our work in soil properties and site characterization. Other current Army requirements that are driving engineering technology include homeland defense, terrorist threat protection, and minefield and unexploded ordnance neutralization. In summary, I believe that DoD and the geotechnical engineering community have had a wonderful partnering relationship beginning in the 1930s. Together, we have conducted research directly related to critical issues regarding our national defense. These results have had dual use application, and by that I mean they've had application to the military and they've had application to the civilian side of the house, the life. The civilian side of the house. They have changed the state of practice in our field, and they have improved the quality of life for all Americans. The system is alive and well today, and as we go about developing our future national defense systems, there are critical roles for the government labs, private industry, and the academic community to play. This is a list of people who have made a major contribution to this talk. I have used their ideas and words freely. I need to call your attention to Ben Fatheree, a history professor at a local junior college, Hines Junior College near Vicksburg, Mississippi. Ben was under contract to the Waterways Experiment Station to develop a history of the geotechnical lab, and much of this talk was taken directly from his history. I also need to acknowledge WES, the Corps of Engineers, and the United States Army. Without their support, none of this would have been possible. This is a picture of Harvey Walls, who guided my career through North Carolina State University and who I owe a great deal of credit. And lastly, to my wife, Margaret, who has built me up when I was down and gently let me down when I was too inflated. And let me thank you too for being a wonderful audience. I'll now entertain questions if you have any, and if I can get the lights so that I can actually see faces. A question that I've often anticipated and nobody's actually asked is, why was the Army interested in underground spherical cavities? But if you think about putting a device dead center and setting it off, you create tension or compression, but no shear. And much of the energy transmitted to the rock is transmitted in shear. And so if you produce no shear, could you conduct underground experiments and nobody know? Now you can use that offensively. We were having treaties to ban underground testing. And you can use that that knowledge offensively to conduct underground experiments and conceal it. Or you can use it the other way to make sure you can monitor the other side of the house to make sure they're complying with the treaty. So that's basically the source of justification for that desire. Yes, sir.
Will you comment on the football-shaped caverns that were dug in the Salt there in Mississippi about this thing?
Yeah. The question is would I comment on the football-shaped caverns? Well, the only comment I can make is that was the first one we had ever built, and we thought we would be more successful if we domed the top to prevent stress concentrations, and it was more proof of our ability to construct it than it was to set off an underground nuke.
So you did put a nuke in it?
I don't know. That's the official answer. Other questions? Yeah.
Are there any major pieces of equipment that are planned for the future at the Waterways Experiment Station?
The question was, are there any major future pieces of equipment that are planned for purchase? The only one that I'm familiar with is we have a multispectral wave generator that is capable of producing multispectral waves in places like the Port of Long Beach or the Port of Los Angeles. And they do plan a major upgrade of that multispectral wave generator. And there might be others that I'm not totally aware of at this time. Yes, sir. The Corps' involvement with space research. I guess the question is, what is or was the Corps' involvement with space research? We certainly built the launch facility at what was Cape Canaveral and is now Cape Kennedy. Much of that's been turned over to NASA. In fact, I'd say all of it's been turned over to NASA. And we play a supporting role, but that's all just whenever NASA calls us and asks for help. We're there, but basically that ball has been turned over to NASA. There was a question back here. Yeah, Bob Patton.
Bill, I had the same question. I was kind of curious if you handle any moon samples or anything at Berkeley or anything like that. Also, before he answers, I'd like y'all to recognize he just finished a term on the ASCE Board of Directors. Did an outstanding job.
The question was dredge material. What we're doing with dredge material, is that your question? What was your question? Moon material. Well, the only thing I know personally about moon material is there was work done at Berkeley. In fact, Jim Mitchell, Nick Costas, and some people like that won a Norman Medal about 1970 on properties of lunar material, and I think there's 5 authors on that paper, and I'm having trouble coming up with their names, but I don't know of anything that we're doing with lunar material now. Again, let me tell you how pleased and honored I am to have been part of this celebration, and I'll step down. Thank you very much.
Thank you, Bill, for an outstanding piece of history and a wonderful presentation. We have a certificate to thank you, and I'm going to read it before I give it to you. It says, a certificate of appreciation to thank Dr. William F. Marcuson III, USA Waterways Experiment Station, for delivering his 1999 Terzaghi Lecture entitled Soil Mechanics and U.S. National Defense, a Mutually Beneficial Relationship, at the occasion of the 8th Spencer J. Buchanan Lecture, November 3rd, 2000, Texas A&M University. Thank you very much, Bill.
Thank you. I will cherish this always. Thank you very much.